And for our last presenter in this opening session, it's my pleasure to introduce you to Mr. Ralph Langner. Mr. Langner is the director of Langner Communications, and he has accumulated almost 3 decades of hands-on experience in the cybersecurity issues of different critical infrastructure facilities. And most of you probably know him for his comprehensive analysis of the Stuxnet malware. It's great to see you here again. He's, by the way, also known as the best dressed man in cybersecurity. And Ralph's keynote will focus on the passive defense. The floor is yours.
Thank you very much. I have failed miserably. I have failed because all the time I was working so hard to establish a credibility for my technical talent, but instead I'm recognized for my sartorial preferences. Anyhow, I think I got to live with that. How many times did you hear the buzzwords artificial intelligence, IoT, etc., how fast the environment is changing? I would like to challenge that concept. Just to the contrary, I pose that our time could be characterized as the dark ages of cyber defense. Why is that? Because you cannot fail to see that some basic assumptions in our space, some basic methods, concepts are very, very static. And this is just like in the dark ages. In the dark ages, people were under the assumption that history is static, that tomorrow would just like be yesterday. And unfortunately, this led to a promotion of methods, also referred to as best practices in our times, that didn't work all that well. So for example, in medicine, the best practice, the standard cure for everything was bloodletting. It was used as a cure against the measles as well as against cancer. Well, I think you can draw a lot of parallels to cyber defense because the asset owners that are operating critical infrastructure, for example, tend to rely on a very basic set of mitigative methods and technologies that didn't work all that well, right? So we positively know that most of these methods and best practices have their severe shortcomings, yet they are still used. And we see the same issue on a conceptual level, because most of the discussion on cyber defense is focusing on the hackers, the evil hackers, on information security, confidentiality, integrity, availability. By the way, let me tell you just one thing, just one takeaway from this conference. When you think about cyber physical, this concept of CIA is almost useless. It's almost guaranteed to drive you into a dead end for a simple reason, because in cyber physical, what you really need to focus on is control and determinism. And as we have seen, is that the concept of information security does not cover that very well. Which leads me to a first conclusion here. Our space is exploding in so many ways that the one-for-all cure, the one-for-all approach should be abandoned rather quickly. So we should rather try to approach all those different focal areas as silos which warrant their own specific methods and concepts. Another would be risk management. Risk management, unfortunately, has shown to not prove to lead to measurable good success. It is usually abused heavily because at the end of the day, it always conflicts with the budget that you have, and this is the time when the decision makers try to argue the threat level away, so that they end up with having to spend less. So risk management is another concept, another doctrine, just like information sharing, that didn't work out that well. And I think it's high time that we should put all those foundational concepts, especially in the area of critical infrastructure protection, which I'm focusing on the stand and just determine if we have something that's more useful. Let me finish with another doctrinal matter. How many of you believe that in the cyber domain, offensive has the upper hand? Raise your hand. Come on, I don't trust you. That's only 5? No, there must be more. How many do believe that offensive does not have the upper hand in the cyber domain? This is what I guessed. You're just afraid to raise your hand and take a stance. So, in my opinion, we'll see that changing. So, one of the conclusions that I'm drawing from the argument that I lay out is that in critical infrastructure protection and when it comes to defending strategic strike systems, the long game will be won by defense. Why is that? In the recent years, we have seen some tremendous improvements in cyber defense, especially in that area of cyber physical. So, for example, as I will tell you in a minute, our capabilities to understand and model complex hybrid systems has grown tremendously. And then we have some new approaches like user behavior analytics, like crowdsourcing, which I will discuss in a minute, that really change the game, even though they are not publicly recognized. And this gets me to another problem. When you think back about those doctrinal issues, as you well know, many of these defensive mechanisms and approaches are also part of international standards and maybe even of regulation. So no matter if you take the recent executive order of the US administration, where risk management is again a key piece in there, no matter if you take the German IT-Sicherheitsgesetz, many of these concepts are baked in there. And this is bad if only for one thing. Once that you have regulation, you can bet that the base which is covered by that regulation, for example, critical infrastructure, they will only do what they have to do in order to become compliant with the regulation, but they won't do anything on top of that. So that would be an example why regulation and why international standards can turn out to be counterproductive, just because you will not be able to take advantage of new developments, which certainly will take years, if not decades, to enter into international standards and regulation. So we need to move at a faster pace, if only for one reason. The offensive side, they are definitely moving at a faster pace. They don't do international conferences on hacking and come up with standards on how to best take down a power grid. They don't need standards. They just use whatever works. So let me give you some examples of what I believe to be significant game changers that will completely turn the table in the future in the area of critical infrastructure protection. The first groundbreaking approach that I see is crowdsourcing. And as far as I know, you even have a special session on crowdsourcing in this conference. I think it really deserves this. So what still many asset owners don't fully understand is that the modern cyber attack campaign doesn't target them as a singular target, but they're just part of the swarm, okay? And what the campaign, the offensive campaign really does is they're going for the swarm, which makes their business so much more efficient. And if on the victim side, you try to fight the offender on your own, you're pretty much lost. It is much more productive to also operate as a swarm. And one way to do that is crowdsourcing indicators of compromise. And this today goes way beyond your dad's information sharing. So we are not talking about exchanging emails, memos, etc. You're talking about automated processing of indicators of compromise. And as I'm confident many of you know, there is a stack of technology solutions to make that happen. You can see them in the lower right corner. The most prominent would be Styx and Taxi. So the technology is there. And why is this significant? It is significant because the time and effort to compromise must not be substantially lower than the time and effort to detection of breach. As you will most likely know, in most cases, the time to detect compromise is around 18 months. How much is the time to actually breach, to compromise the target? Well, maybe a couple of days. And when it comes to critical infrastructure, we don't have that luxury. We must be able to act within hours. The clock is ticking, okay? And we can only, or we have a good shot at actually achieving this if we use these modern methods that allow us to act much more quickly, even before fully being able to analyze the threat, to analyze the specific malware and to do some attribution. Just to give you an idea, I was working on Stuxnet for 3 years to fully understand what it was doing. In critical infrastructure protection, you don't have the luxury. You must act within hours. Okay. Therefore, I suggest that we separate the discovery of a breach from the forensics and from the attribution. So the crowdsourcing really makes sense when put together with security automation. Last year, we had a milestone event in security automation, and that was the DARPA Cyber Grand Challenge. Now, for the first time in this challenge, which used to be a hacker competition, for the first time last year, DARPA had different hacking teams compete against each other to breach their systems and recover from breaches. But the novel thing was that they weren't allowed to manually interact with the computers. So it was all pre-programmed. And if you want to, you can also throw in the term artificial intelligence here. Okay. So the teams used algorithms to invent new offensive approaches against their targets, and also algorithms to recover from experienced cyber attacks, to auto-patch, as an example. Now, why is this so significant? I think it's going to take maybe a couple of years more before this can be put to practical use. But I think it is so significant because if you believe we will be able to raise the level of competence in our workforce to the degree that we would need it, you're very much mistaken. This space is exploding. If nothing else, it's exploding in complexity. And human experts are today even no longer capable of actually taking care of every single breach and responding to any attack. So I would certainly agree that developing the workforce of cyber defenders is essential, but let's not fool ourselves. This will never be enough. And the only technology or approach that can save us is security automation. So I suggest to heavily keep focusing on this. The battles will not be won or lost by humans. They will be won or lost by algorithms. The other positive development that I see, where we have seen tremendous progress over the last couple of years, is advanced analytics of hybrid systems. Actually, these applications and this approach is, in my opinion, becoming commonplace. So, for example, what you see on the left is Palantir, the Palantir software. I think many of you will be familiar with that software. In the middle, you see Maltego. I would just assert that if you're doing any kind of social engineering and if you don't use Maltego, you're doing something wrong. And on the right, you see the software that my company is developing, which is specifically for cyber-physical systems. And we have made tremendous progress in being able to model these complex hybrid systems. In the case of cyber-physical, it's even not as difficult as you might think, because maybe the first thing that pops in your mind is, well, all those legacy systems, those funny PLCs, etc. Yeah, they're a bit strange, but at the same time, the complexity is way lower than you find in any average IT space. So, for example, you should consider that in a regular power plant, you're talking about roughly 1,000 digital components that control the plant. Or if you want to scale it to a large power grid, in the United States, the power grid consists of 55,000 electrical substations. Well, that might sound as an impressive number at first, but if you consider the computing power and the algorithms that we have today that we can use for modeling and advanced analytics, you'll understand, well, that's doable. We can do that. We can make that happen. We can analyze every single attack vector before it happens. And as you know, every battle is won before it even starts. If anywhere, this applies to cyber-physical systems. Let me tell you about these advantages that we have in cyber-physical. The cartoon right here lets you understand the concept. Everybody understands that this doesn't work. You cannot hack a toaster, even if it would be an IoT toaster. You cannot hack the toaster and turn it into a blender. It just doesn't work. And this is something that I learned many years ago when I started to do my first assessments for asset owners in the industry. And me and my team, we were always coming up with bizarre scenarios, but what if we do this, and what happens to this process? And most of the time, the response from the asset owner was, from their engineers, oh no, that can't happen, it's impossible. Well, certainly back in the days when I was a bit younger, I was thinking, well, they're just cheating us because they're afraid that we have just spotted some significant risk. But then I learned they were actually correct. So the key here to understand is low entropy. Physical systems are low entropy. There isn't a lot of states that they can be in, just by the law of nature, okay? Let me explain that in an example. What you see on the left are valves, actually, from the Natanz uranium enrichment facility. And those typical binary valves, they can only have two states, open and close. And they only have two failure modes, which would be cycle or stick. There is no in between. This is low entropy. You see the same thing with electric relays on the bottom right, okay? And the same is true for the process as such. Now, get this, just as an example, the process of producing electrical power usually can be boiled down to boiling water. It's not really complicated. So most physical processes used in critical infrastructure are surprisingly simple and static. And this allows us to actually model the whole process, the equipment, and any cyber angle that we could use to attack this specific facility and process. And this brings us to some very interesting questions, like, is it possible for a given safety architecture in a nuclear power plant to melt the core by a cyber attack? That's a technical question. It can be answered by technical analysis. And it's not even extremely difficult to do that, because we have the luxury that everything which has to do with safety, especially in high-profile targets like nuclear power plants, is already analyzed, and that analysis is publicly available. So we take that safety analysis and now just throw a couple of scenarios against that structure and see what we can do. Let me talk you through this specific example, because I think it's easy to understand. In a nuclear power plant, well, most people know that you run into trouble when the reactor overheats, because it doesn't get more cooling water. What most people don't know is that the adverse is also true, because if you shock cool the feed water, then you're going to overpower the reactor. Because this is known, the feed water is heated before it is sent back into the reactor core. So there are a bunch of heaters in a nuclear power plant. You see one on the left corner in that picture. That's a feed water preheater. Now, in a typical nuke plant, you have a bunch of these feed water preheaters. Let's just say 15. And when you look at a specific safety analysis for a specific nuclear safety design, they do address the scenario that a feed water preheater is taken offline just by random failure. Okay? But the thing is, there is more than this one feed water preheater, and all of these heaters are connected to what we call normal process control, to just a normal control system. It has nothing to do with a safety system. So here is my scenario. With a cyber attack, it is extremely easy to bypass redundancy. In the physical world, redundancy is a big deal, because if you only consider random failure, then the odds that all of these heaters would suddenly be taken offline for some reason of nature, that is extremely remote. But in a cyber-controlled environment, the story completely changes, because the cyber offender certainly had little difficulty taking out all of those heaters, okay? And certainly this is what they would want to do. And then you can overpower the reactor, and in a couple of minutes later, you would be able to melt the core. And so why am I pointing this out? Not to scare you, or only just a little bit, just a little bit. Because I have the good news. The good news is we can analyze this. We just need to do that. So we can find the systemic vulnerabilities in cyber-physical designs and then mitigate those vulnerabilities. We can do that. Unfortunately, usually what we see in critical infrastructure, it is not addressed. Cyber is not appropriately addressed, and many people are under the misconception that once that we have safety systems in place, we are good. What I just tried to show you is that even if I have an analog safety system in place, which I cannot hack, I can still cause trouble. This would be a more detailed sketch, but we don't need to go into the details here. I just want to give you the idea. We can model this, we can analyze this, and once that we have done that, we can fix those vulnerabilities. One way to fix those vulnerabilities would be employing analog control. Look at the two cars in these pictures. Guess what? All of you have heard about car hacking, right? One of these cars cannot be hacked. Which one would that be? Which car do you like better? The cool Tesla or the old-timer? Well, I can tell you I like the old-timer better, if only for that reason, because it cannot be hacked. Why can it not be hacked? Because it doesn't include any digital control. So I'm not arguing that we should go back to relays and hardwiring. It's not what I'm arguing. I just want to point out that this is a research field in its own right, where companies and research groups are developing state-of-the-art control systems that cannot be hacked. One example would be a Westinghouse safety system that you see on the right. It's FPGA-based. Another example would be a very innovative product by a team led by Tim Roxy. It's called Operation Rock Ridge. Tim Roxy used to be the CSO of NERC, the North American Reliability Corporation. Now he's the head of the EISEC in the United States, and he's leading this effort to build these tiny analog control systems, which are unhackable. So for our most critical spots, we would really like to use these for obvious reasons. Now, here is my idea how to put this all together. What I want to communicate is that we are going to see tremendous advances in cyber defense in the cyber physical space, which affects the critical infrastructure, and it also affects strategic strike systems. So the technology will be there. This will completely change the game, because offense in that space will no longer have the advantage if we are smart, if we do our job. And I think the tough part is, certainly it's not that easy. I don't want to fool you. It still is tough. And it's tough because policy needs to step in and define the areas where we absolutely cannot tolerate compromise. And I have indicated those in the bottom, in that red rectangle, where a consequence of compromise is unacceptable. And the good news is that in cyber-physical and critical infrastructure, strategic strike systems, this is a narrow field, okay? We can do that, we can make that happen. But policy needs to define the red line, or the Pentagon also refers to it as the thin line. I think the recent report by the Defense Science Board from this year, it's from the Task Force on Cyber Deterrence, is maybe the best policy document that I have read so far by the Pentagon on cyber defense. I highly recommend this paper. You can either Google it or just go to my Twitter feed. It's Langner Group. And just recently I tweeted about that paper, so you will also be able to download it with a link from there. So this needs to be defined by policy. Where is that thin line or that red line? And then the technologists like myself can make it happen. We can make those systems so super secure that the attackers, even those evil Russians, I hope nobody is here from them, won't technically be able to actually compromise those. Then we have an area in between where consequence is critical, but you can't defend against all possible threat actors. So you want to make your triage and just want to make sure that only the top tier threat actors could probably achieve some effect there. And then in the blue space, we have the area which we seriously just cannot defend in any meaningful way, so that's the area where the Internet of Things comes in, or as the US Army is presently working towards it, the Internet of Battlefield Things. It's actually happening as we speak, the Internet of Battlefield Things. So certainly you can try to take advantage of these positive nonlinearity effects of the anti-fragility, but we will not be able to defend this area with any reliability. We will be able to do that at the bottom. And with that, I just want to finish with that positive outlook. The long game in critical infrastructure will be won by defense, and I hope to see you on the battlefield and fight that fight with me. Thank you very much.
Thank you.
Thanks.